I will continue working on this thing, and it seems that I can't get collected to work on it without recording. So recording this kind of makes a boring video. I'm kind of sorry about that, but at the same time, it gives me the opportunity to see what I have done later, why I made certain decisions that I did, and maybe it it gives the other people that I'm talking to a realistic presentation of how much work I'm putting into this. Because a lot of times I have the sense maybe that people are just kind of reading what I'm saying as though I made some kind of knee-jerk reaction. And usually I try not to do knee-jerk reactions. I think things through quite a bit before I post a response, and I just want to give kind of a sense of how much I'm kind of thinking about it and working on it. So anyway, this pattern here kind of surprised me. I don't want to do this pattern. There is probably some better solution for doing this, but I'm wanting to create a pattern that's kind of triangular like this one, and the numbering scheme goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and coming up with a way of going through those for the horizontal lines and going up for the vertical lines is not not exactly as trivial as I would like it to be. But I am looking for a pattern that will work. For instance, I think since this is a string of odd numbers, this could be represented as 2 squared, and this over here, 2 squared plus 4, 2 squared plus 2 times 2. Let's call it that. Plus 2 times 2. And the next one would be 3 squared will be 9. And this will be 3 squared plus 3, 2 times 3. Plus 2 times 3. So we could create a table of lines of e-grids, each one starting at I squared and going to I squared plus 2i. And in this, I want I to go from 1 to Euclidean grid density. So then I can just erase all this because that is what I will just get that out of that table, hopefully. And it might be that I can, yeah, I don't need this or this. And let's find out whether that works. I sure just deleted a lot if it doesn't. Okay, it didn't want me to use EU grid dense, but it was perfectly happy with EU grid dense minus 1, and that produced that line right, that group right there. All right, next I want to work on the next list, which had like 4, 6, 8, 10, 12 plus I. So it turns out that I can just add 1 to L here, and it gives me 5, 7, 9, 11, 13. So it does add 1 to each number in the group. Another thing I want to do is see if I can, I don't know, pop L. That's not a word. Shift, uh, reap L. Um, and that gives me 4, 6, 8, 10, 12. Oops, it added something to it. Discovery. This is how I get things off the front end of the list. The -1 position refers to the last position, and 2 refers to the second position. So if I just go 2 semicolon semicolon -1, I get everything except the first element of the list. That's cool. So I'm going to define a list called pluses. And plus is going to be a table that goes 4 plus 2i to get 4, 6, 8, 10. And I'm not 100% sure what this needs to be, but I'm going to try going from 0 to Euclidean grid density minus 2. Actually, that's really not what I want at all. Probably. I don't know. The first pattern I need starts with 0 plus I, 4 plus I, 4 plus I, 4 plus I, 4 plus I. The next one is 6 added to everything past here. Then 8 added to these two. Then 10 added to these two. And then the last one is 4, 6, 8, 10, 12. So what if I created a list containing the number 12 and then added 10, 10 to that list after pushing that over, and then push this over and add 8, 8, 8 to that list. I'm going to need to learn a function that pushes a list over. Okay, so I've written a function. It's a little bit complicated, but we're going to start, like if I put in min max being 4, 12, what this would do would it start out with out being 0, 12. Then we would increment it, or no, we wouldn't increment it. We just defined this other thing being increment equals 1, 1. So we start with plugging in I equals max minus 2, that would be 10. We'll say, and this will continue until I is less than or equal to 4, which was our min. I minus equals 2 should subtract. So we're starting with 10, and then we'll subtract and make it 8 a little bit later. So right now, out equals out plus I times increment. So it should be adding 1, 1 to the increment. I think actually, based on what I did a little while ago, I could just leave increment be 1, and it will add 1 to every element in the list. And then I would not have to concatenate 1 with the increment later. So I don't have to change increment at all. So now, so out equals out plus I times increment, we'll be adding 10 to 12 and adding 10 to 0. And then out gets concatenated 0 with out, which means we're going to add a 0 over here. We're going to repeat the process after subtracting 2, so we'll be adding 8 plus 10 plus 12, 8 plus 10 plus 0, 8 plus 0 plus 0. And then at the end, when we get all the way down to 4, because I is less than or equal to 4, it should be out equals 4 plus 6 plus 8 plus 10 plus 12 over here on the right side. And that should give us out. So what that will do is instead of this here, all of that we can replace with some list of 4, 12. If that works, that simplifies things somewhat. Actually, we need egrid I plus some list 4, 12, and we need to find another side to that. Is it right there? I think so. Maybe it's over here. And, oh, and then we have table. What? Maybe that'll work. Or maybe we need 4 brackets over here. Okay. It did not do it. There's something that is an error. Let's see if I can find it. Maybe it's this use of less than or equal to when it really should have been greater than or equal to. For some reason, our sum list code is producing the output 0, 12 null. Now I can see why it is producing the 0, 12 from right here, but I think this calls for a manual treatment. I did out equals 0, 12. Out plus 10 definitely gives us 10, 22. Concatenating 0 with out plus 10 definitely gives us 0, 10, 22. But I actually want to change out equals out plus 10, and then out equals concat out 0 with out, and then out equals out plus 8. Oops, what happened? Whoops, I got out equals on the wrong line. In any case, I can get rid of this line with the increment in it. It's not necessary. So that can go away and make that into nothing. It's the comma. Comma instead of a semicolon. Okay, that was a half an hour. There we go. My gosh, that took a long time. Okay, use commas where commas go, semicolons where semicolons go. And remove my print statements, unnecessary print statements, and that checks should work now. And then this one, I'll just replace that with I plus sum list. And this one will be 6, 12. Not quite perfect. And then instead of 12, we should have 2 times parentheses E, what is it called? Euclidean minus 1. I've also got to establish a pattern for the 1 and the 4. The 1, the 3, the 4, the 8, the 9, the 15. Which on this side is going 1 plus 3 is 4. And 4 plus 5 is 9, and I would imagine it goes up to plus 7 at that point. So actually, 1, 4, 9 is 2 squared, 3 squared, 4 squared, so 16. And then this would be over here. So this side is basically an n squared, and this is an n plus 1 squared minus 1. And I think n here is just the Euclidean grid density, or it will be at the top layer. And then it's just a question of where does n come into play over here, recalling that n is 1 here, and n is 2 here. So I'm thinking this is going to be 2n plus 2. And I'm just going to use 1 and 3 over here. So this will be still the same thing. I'm just going to skip 2 for now. And so we'll have not the central line won't be rendered for the moment. Or maybe not. You know what? I think I'll just call this 1, 2, 3 right here. And I'll go ahead and do the first one normal like 1, 2, 3. And this will be just 4. And then after that, I'll do a do loop here. or maybe a for loop. But this time, let's try to make sure that I use commas in my for loop. For n equals 2, because we're going to start with 2, and was technically 1 right there. For n equals 2, comma, n less than or equal to, I think, Euclidean grid density, comma, n plus plus, comma, and we're going to do EU spacelines equals concat EU spacelines, which was defined up here. And we're going to create a table just with two entities, one at 2 and one at 3 squared minus 1 is, or no, 2 squared is 4, and 9 minus 1 is 8. And then we'll do, so that would create a bunch more lines. And just to be on the safe side, let's put a minus 1 here and see what pops up. Well, it was successful to there and there, but then for some reason it stopped when it got to there. Oh, right, because this needs to be made 2n plus 2, and this needs to be made into U grid dense minus 1. Well, that didn't quite do it. So what else can I do? Copy this line accurately 2 times. And that filled out everything that we could have filled out. Maybe I have, for some reason, maybe I should need to go to Euclidean grid density minus 2. See what that comes up. Ah, perfect. Great. And now let's increase the Euclidean grid density by changing the events per Hubble observer to, say, 11, and see if it still works. Oh my gosh, it does. That's fantastic. And just for fun, let's change this to 17 and see how that looks. Oh, no, that's not going to have any effect on this thing. What I want to do is, I don't know, render the other lines as well. The red, and change this to blue. Red is not a good color for these. I want my Euclidean coordinates to be blue. And blue. This stuff can all probably go away. Where is... Oh, I see. Yeah, what about my black ones? Here they are. Put those back in there and see it all together. The lovely. So there are some things that this approach could do better, and I probably just this method is almost the fallacy of sunk costs at this point. I want to just keep doing it now that I've put so much effort into it. But I might decide that it would be better to just find another method of generating the lines based more on, I think, actually, you know what I want to do? I want to make this Euclidean coordinate system go out as close as possible to the edges of the map, so that we have the Euclidean coordinate system coming down almost to a point down here and going up at the speed of light from either side, but still they should be able to go, yeah, because between these points you can have the speed of light, but they're not necessarily at the edge of the particle distribution here. And as long as those events are not right at the edge of the particle distribution, then we should be able to get our swing down function to work. What was that function? Swing down, fold out, not swing down, fold out. Maybe, let's look at what it looks like after the fold out. Looks kind of like that. Oh my gosh. Some of those look very strange. You know what? I need to make those different colors. That could be the problem. So we'll call the timelines blue and then green for the Euclidean spacelines. See what happens then. Then we've got, oh man, it's really hard to see. But plugging in 30 and 30, what I'm seeing here is that these Euclidean timelines are literally wrapped around in this space so that it's not just swinging them down, it's actually warping them into so that these events look like they are preceding these events. But all right then, I'm going to wrap this up and write my I'm leaving now text. You can already see that I've written this many times. I'll just write it again right now. Here.